komponent. Alla elektriska komponenter. Det här är en komponent. Jag tror det menar nej, det är ju...
All right, so let's get started. So we will continue today, again in the physical layer, but slowly moving up from that. And at the end of this week, we should be firmly up in the data link layer again. So the idea today is to wrap up a few things about modulation that we were unable to finish off last week. And then to continue to talk a little bit about something called error detecting codes. And we will start by talking about binary block codes in general. So last week we spent a lot of time dealing with pulse amplitude modulation to figure out how to transmit bits over a Gaussian channel, a noisy channel. And we calculated the error probability for pulse amplitude modulation if we use M-ary modulation. And the expression here is done in terms of a Q function, where the one important parameter is ES over N naught, where ES is the energy per symbol, and N naught is a property of the channel, how strong the channel noise is. And then this expression then also depends on M as we see it here. And the end result, the overall result, one would say, is that the error probability goes down when ES over N naught is large, when this is also known as the signal to noise ratio per symbol. As that increases, performance gets better. Another thing which happens is that when M is increasing and everything else is fixed, then performance gets worse. So when we're trying to push more bits through the channel per symbol, this will result in a higher error probability, or maybe it's the other way around. To get a certain error probability, we have to invest in more in ES, energy per symbol, and that translates to a larger transmit power. Okay. In practical schemes, we often use these QAM constellations, which we can see as two PAM transmissions in parallel, one on a cosine carrier and one on a sine carrier. And then we get a two-dimensional constellation, and with some calculations we can arrive to the corresponding symbol error probability over a Gaussian channel. Looks like something like this. And here the total number of points in the constellation is the number of points along the horizontal axis times the number of points along the vertical axis. So MI and MQ, we can play around a little bit with that, and we can get different results here. And here's the end result. And what one can say here is that if one would compare these two schemes, this scheme is more power efficient, in the sense that if we want to transmit a certain number of bits per symbol, we require less power for QAM compared to PAM in general. Obviously, when M is equal to 2, it doesn't matter, but it's more when M is greater than, say, 4, then this kicks in. Okay, so a message or a thing we should carry with us is that transmission over channels is not error-free. We will always have errors. Okay. So we need to be able to deal with this, otherwise our system will not be very good. And the errors we have talking about now is symbol error probability. That is, a symbol error occurs when the receiver thinks that another symbol, that is another amplitude, has been transmitted than the correct one. And this also translates to that the number of bits will be an error. So there is a relationship, even though it's rather complicated actually, between the symbol error probability, these type of expressions, and the bit error probability. So the bit error probability is that if we take a bit at a random, a bit at any position at the transmitter and look at the corresponding decision at the receiver, what is the probability that they differ? That's the bit error probability. Okay. So if we transmit then k bits per symbol, so m is 2 to the power of k, then if we make an error, symbol error, this means that there will be at least one bit error as a result, right? So every symbol error leads to at least one of these k bits will be decoded wrongly, but not necessarily all of them. So at least one bit error will be an error, and at most k of the bits will be an error. So if I transmit k bits as a block, if the block is decoded wrong, then at least one bit is wrong, and possibly up to all the bits in that packet. Okay, so for instance, if we transmit 3 bits, B0, B1, and B2, and then there is an error that occurs on the channel, then we know that the block of bits are not the same at the receiver as in the transmitter. But it could be, for instance, that only the first bit is in error, the vertical bar here for flipping it, but the other bits might be right. B1 and B2 might be perfectly okay. Okay, so the probability of this event is the probability of a symbol error. However, that's not the same thing as saying that the first bit is in error. Say it's not the same event as one of these bits is in error. Okay. How many errors can we have in a pattern? Well, we need to have at least one when there is a symbol error, but up to 3 here, right? So the number of bit errors we make here is a number between 1 and 3. Okay. So different types of symbol errors will then introduce different number of bits being in error. So in the extreme case when all bits are wrong, so whenever we make a symbol error, all of these bits are wrong, then the bit error probability and symbol error probability is the same, right? In the other extreme case, when only one bit error, only one bit is in error every time we make a symbol error, then only 1 out of k bits are in error, and then the bit error probability is 1 over k times the symbol error probability. So in general, one can say that we're somewhere in between these two extreme cases. We must have at least 1 bit error and at most k bit errors, and in reality we're somewhere in between. So one can bound the bit error probability. It's less than the symbol error probability, but it's larger than the symbol error probability divided by k. Okay. And what we have actually for a given system depends on the system itself, its constellation, and how we assign bits to symbols. Okay. So and actually the exact expression could be quite complicated, so sometimes we just have to be content with these two bounds. So we're not sure what the bit error probability is, but for sure it will be less than the symbol error probability. So the bit error probability will be less than these numbers that we can compute. But we also know that the bit error probability for sure will be equal to the symbol error greater than the symbol error probability divided by k. So again, if we can, oops, wrong way. If we can compute these things, we could just divide them with k, so the log 2 of m, and then we get a lower bound for the bit error probability. All right. Now, if one is concerned about bit error probability, which is not always the case, right? Because what we will see later on is when we send a block of bits in a packet, we don't really care if one bit is in error or all of those bits are in error, because that packet is then broken and it's thrown away anyways. So the consequence of a bit error probability is not so important for a system like that. Then symbol error probability turns out to be more useful metric. But if we are concerned with bit error probability, then for sure we would like to hand out the bits on the constellation in a smart way. And what we would like to do is to make sure that the most common errors, symbol errors, results in 1 bit error only, because that's the minimum amount of bits that could be an error. Okay, so here's a formal proof of what I hand waved you through. If you're interested, you can look at this. But the mapping of bits onto symbols, the standard way to do that if we're concerned about bit error probability is to use something called the gray code. And this works well for QAM constellations and PAM constellation. I would like to warn you that it's not applicable to all possible modulation formats that exist out there. But for the purpose of this course, when we're only going to talk about PAM and QAM, it works well. Okay, so the idea is that when we have a constellation, like an 8 PAM constellation, something like this, where we have 8, now it happens to be 16 points, okay, so it's 16 QAM here. So when we transmit, say, this symbol here, we need to give it a label, 4 bits, so say it's 0, 0, 0, for instance. Now, what is the most common type of error, symbol error we will make? Well, we know that the decision regions will look something like this. So if we transmit this symbol, the most likely error will be to go to this neighboring point or to that neighboring point here. So what I would like to do then, ideally, is to make sure that there is only 1 bit that differs between this label and the label down here, and 1 bit which differs to that label. Okay? And then I want to continue that type of thinking. So neighbors only differs in 1 bit position. They have to differ, right? Because they can't be the same label. But the minimum amount then will be to differ in just 1 bit. Okay, so that's gray codes. And if we do that, then the bit error probability is then roughly 1 over k, or log 2 of m, times the symbol error probability. And that happens at least when the signal-to-noise ratio is relatively high. So almost always when we make an error, we go to the neighbor. We seldom move across the constellation. Okay. So how to do this for a rectangular one is that it's very simple. One starts with using a gray code in this dimension. So here we see that we need 4 bits now, but we need 2 bits along that dimension. So we start with some arbitrary number, say 0, 0, and then we just flip 1 bit, 0, 1, and then flip 1 bit. Not the same bit, obviously, right? Because there has to be unique labels. So it's 1, 1, and then we only have 1 left. It's 1, 0. Okay. So we do that, and we put the same thing on the vertical axis here. And then we enumerate this point by taking those bits, 0, 0, in the beginning, and then 1, 0 at the end. And then we get this label. And then we continue the whole row here. So we see that all of these, the first 2 bits here, is the bits that we read off here. So 0, 0, 0, 1, 1, 1, 1, 0. And all the last bits is 1, 0. Right. And then we just continue doing this. Oops. And then we get a gray code on the QAM constellation. So it's not very difficult to do, right? And for larger constellations, this specific order of labels here, one can do that in many different ways. So there actually exist many different types of gray codes. However, this one is known as the binary reflected gray code and happens to be a fairly good one. Okay, questions? No? Okay. So let's continue then, and then so what we have talked about is now how to transmit bits over a channel. And the question is then, how should we be able to handle errors at the receiver in these bits? And the standard way to do that is to use error detecting codes. So we detect errors in a packet, and if that happens, then we ask the transmitter to resend the packet until we get a packet which we think is correct, and then we accept that. Okay, so if we think of this as a layering structure here, the receiver gets some bits and it inspects that, and if the receiver thinks it's bad, then he asks the transmitter to send the bits again. Okay, and this is done primarily through something called error detecting codes, which is a special case of codes. Okay, so, and we will talk here in this course about binary codes, and the concept is quite simple, but also in its all simplicity could be quite complex how to construct codes. So we will take this in steps now. So what we have here is a block with an input and an output, and this is called the block encoder. And what the block encoder does, it takes a number of bits as input, in this case k bits, so from 0 up to k minus 1, k bits here. And then it maps that onto another sequence of bits. Okay, so there are bits in and bits out, but the number of bits out is larger or equal to the number of bits in the input. Okay, so the number of output bits here is small n, and this is the n here, and the number of input bits is small k, so that's the number of input bits. So this is called an NK block encoder. The input bits here, we call them information bits. These are the bits which belongs to the payload, the data, user data that should be transmitted. And then we denote them by small b, and m is the mth of those. So it's zeros and ones. If we put them together into this vector capital D, boldface D, these bits here, that's called an information bit pattern, or information bit word, or information bit vector. It's the same thing. So vector, word, or pattern is the same thing. We will call them word as often as I can remember to say the right word here. Okay? So this is the information word, the payload. The output here, the individual bits here are called code bits, and the whole block is called a code word. And we see that the code word has n bits, the information word has k bits, and n is greater than k. So the code rate is the ratio between the number of input bits to the number of output bits. So this is a number that specifies how many information bits there are per code bits. Right, so that's the interpretation here. Now, for efficiency reasons, we would like that the expansion, the number of added bits here in the block encoder, is relatively small, because these bits are then later on fed to a modulator and transmitted over the channel. And we know that the more bits we need to transmit through the channel, the more costly it will be in terms of either bandwidth or power, or both. Right? So we would like to limit the number of bits here, but still retain some good properties of this. And the good properties, we will talk about what that is in a moment. Okay, but k over n, the code rate here, is a number which is less than 1, right? Because n, well, it could be 1 also, but n is always greater or equal to the number of input bits. And the reason for that is that the block encoder cannot lose data, right? So if we have k input bits, we better have 2 to the power of k possible outputs, and that means that the number of output bits here needs to be at least k bits, right? Otherwise, we will not be able to represent all inputs in the output. This is interesting. I got my wrong notes with me, so I have to hand wave my way through a few things here. Okay, so let's try that. Let's consider an example of a block code. So we need a number of inputs, and say that we have B0 and B1. And then we need a number of outputs, and say that we have 4 outputs. C0, C1, C2, and C3. Okay, so how many possible input patterns do we have? Well, we have 2 bits with 4 possible inputs, and let's just list them here: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and then we need to assign bits to the code word here, and we can do that in many different ways, right? So we have 4 bits now. So we have, how many output patterns do we have to choose from? 16, right? But we only need 4, right? Because there are 4 in the input. Okay, so we have some freedom in choosing the outputs, right? And let's just say that the 0, 0 maps to 0, 0, 0, 0, right? 0, 1 to 0, 1, 1, 0, say. 1, 0, 1, 0. Sorry. Let's do this right. 1, 0, 1. And then we have 1, 1, 1, 1, say. So that's a possible block encoder, right? Number of input bits is k, and the number of output bits is n. So what is the code rate for this one? It's not rocket science. It's either 2 or 1/2. That's the only thing we need to figure out here. So it's 1/2, right? So, okay, so that's an instance of a block encoder. The set of code words is called actually the code. And we denote that by curly C. Okay? So it's the set of codes, C0, C1, C2, and C3 in this case, since we had 3 code words. And that's simply, in this case, equal to 0, 0, 0, 0. That's one code word. Second code word is 0, 1, 1, 0. Third code word is 1, 0, 0, 1. And the fourth code word is 1, 1, 1, 1. Okay. So that's codes in general. Now, for practical purposes, we are often interested in having some structure into this code because we want to efficiently be able to generate the mapping from the input bits to the code word. And as we later on, we would like to see also that we would like to have some nice structure into this so we can use that efficiently. Okay. So one way to introduce structure is to use something called systematic codes. And systematic codes are codes of this with this particular structure. So the input is the same as before, D, and the output is a code word. Now the code word has a specific structure that the first k bits is equal to the input bits. Okay? So we just copy the first k bits into the code word, and then there is an appended number of bits, which are called parity bits or check bits in the P vector here. So systematic code words have code words which are of the following form. We have the first is the information bits, and then we have the check bits. Okay? So how to do encoding here is that one simply take D here, and then output that here, and then put that to the output. And then we have some box that calculates the parity bits depending on the information bits. And it's called the check bit calculation box or parity check box, parity bit calculation. And then we have P here. How many parity bits do we have? Well, since the whole code word has to have n bits, and the first k bits is the data, then what we have left here is n minus k bits. Okay? So these are the parity bits. The fewest number of parity bits we can have, I guess, is 0. It's not very interesting. So we have one could have 1 parity bit, 2 parity bits, or 3 parity bits, or whatever. Now I should say P0 and P1 here. I need to fix that when we get home. Okay. Here, this particular code, is it a systematic code?
Maybe you
you have flipped the number and then...
You see the structure here, right? But the only thing that matters for the question of whether this is systematic or not is that if the first bits are the information bits, and we see that that is the case here, right? For all of these keys. So this is indeed a systematic code. Then these are calculated somehow. Now you already decoded it and see it's actually the information bits in reversed order, right? But that just happens because I made it up on the fly here, more or less, right? But that's one way to do it. We could do it many different other ways. So indeed, this is a systematic code. Okay. Now, we want to use these type of codes in order to detect whether errors have occurred in transmission. And this is from the perspective of the receiver. The receiver has no clue of what data was sent, right? That's the nature of things. But it gets some bits out from the demodulator at the receiver end, and then it needs to inspect those bits to figure out whether an error has occurred or not. So now, suppose we are the receiver, and we know that this code has been used. So, I mean, the transmission goes something like this. We have the information bits coming in here, and then we have our NK bit encoder, and then we get out a code word. And the code word we get depends on, it's indexed by the input bits. Then this is sent through a modulator. To generate a transmitted signal, an analog signal. So this could be pulse amplitude modulation, QAM, or something else. Something, right? And then we have a channel, and usually there is some noise on this channel. And then we get to the first block in the receiver, which is the demodulator. You know, the matched filters, samplers, slicers, and all these things, right? And we stick everything into this block that we call the demodulator. And the output from the demodulator here is then bits. Ideally, it should be the same bits as we transmitted, right? And let's call these output bits Y here. Okay, so here we had, this is N bits, and this is K bits. And here again, we have N bits. Now, we also know that there will be errors occurring on the channel because we have noise here, and it's impossible to guarantee error-free transmission as long as we have a little bit of noise. And how we can model this is that we take everything which is inside here, all this analog stuff here, and we replace that with something that introduces errors. Okay? And the block diagram for that is quite simple. It should have the same input-output as before. So the input should be the code word, whatever code word we chose to transmit. And then something happens on the channel, and then we get an output bits here. And what happens on the channel is that we add on an error pattern, where this addition here is modulo 2. So the output Y is equal to the input modulo 2 added, with the plus with the ring is modulo 2, to the error pattern E here. And the error pattern is a binary vector with the same length as the input, that is, the same length as the code word, that is N bits. And let's call these bits E1, E2, up to En. And when these bits are 0, that means that no error occurred in that position. When these bits are 1, that means that errors occurred in that position. And why is that? Well, it's because modulo 2 addition, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 0, and 1 plus 1 is equal to 0. So if we think of this as the corresponding input bit, say Cj, and this as the corresponding error pattern bit Ej, we see that Cj changes its polarity whenever Ej is equal to 1. That's the nature of modulo 2 addition, or XOR if you like. So if the input is 0 and the error pattern is 1, then the output is 1. If the input is 1 and the error pattern is 1, then the output is 0. Okay? So this very simple formula models what's going on the channel, right? So the noise introduces some errors in certain positions. We put that into the E vector, and we add the E vector to C to get the output Y. Clear? Okay, so very nice. We have abstracted things. Now we want to do error detection. And error detection means that looking at Y, trying to make a decision whether to accept Y as a valid code word, a valid transmission, or a transmission where error has occurred. So how are we going to do that? Let me ask you this. If Y is equal to 0, 1, 1, 0, would you accept this or not as being an error-free transmission? How many would? Hands up. 1. How many would not? 1, 2. And many uncertain. Okay. Let me, before saying the answer, if I say that Y is equal to 1, 1, 0, 1, would you accept this? Or not? I mean, how should we go about to do this, right? We can't just stare at the number of bits and say, oh, it's error, clearly error, or clearly not an error, right? We need to use our knowledge. And what is our knowledge? Our knowledge is we know that there is code words being transmitted, right? Which means that not all possible bit patterns are transmitted here. We're transmitting 4 bits, right? But only 4 patterns, which means there are many patterns that we never send. So to check whether an error has occurred or not, one can look at the bit pattern here, 1101, and then we go in. Can we find a code word which corresponds to 1101? No, there is no such, right? So here, for sure, what do we know? An error must have occurred, right? Because this could not possibly be sent, right? Because the sender sends a code word, and this is not a code word. Hence, an error must have occurred. There is no other explanation. And when that is the case, we throw away the data and we tell them, the transmitter, could you please send the data again? I don't believe I received the right answer here. Okay. This pattern, what do we do? Well, okay, we look here, 0110. Okay, here, looks good. It's a code word, corresponds to the information bit 01. We could already have read that off in the beginning because this is systematic code. And then we will accept this as being an error-free transmission. Now, let me ask you this question then. Is that safe to assume that no errors have occurred? I mean, it's a leading question, and the answer to this is no, right? Because what could have happened is that we could have sent the 00 code word, and it happens to get 2 errors in the middle, which means that we receive another code word, but not the code word that we transmitted. Okay? So the only thing we can say here is that Y is a code word, that is, it's in the code, and therefore things look good. But we're not absolutely 100% sure that things are good. Okay? So did you follow this? Because this is important, right? Because this is the basis of error detection, is that we look at the received pattern, and if it's in the code word, we accept. If it's a code word, then we accept it. This acceptance could be wrong, right? We could accept a code word which is not the transmitted code word, because errors can move from the transmitted code word to another code word. However, if it's not the code word, then we know for sure that error has occurred. And this we can do with 100% accuracy, right? Because if we receive something which is not the code word, when Y is not a code word, then we know that errors have occurred. So the errors goes this direction, right? The implication cannot go the other way. All right? Okay, so a block diagram for showing everything here is something like this. So here we have the transmitter, we have the channel, and here's the receiver. The receiver in the sense that it tries to figure out whether to accept the transmission or not, to do error detection. And now we use systematic codes here. So we use a systematic encoder, which means that the transmitted code word is the data plus some parity bits, some check bits. We go over the channel. The channel introduces an error pattern. If the error pattern is all zeros, that's fine, because then no errors have occurred. Otherwise, there will be ones in this error pattern at the positions where errors occur, which means that the received word can be written as the transmitted code word plus the error pattern. Or if we split that up into 2 parts, it will be some error pattern which affects the data bits, and some error patterns which affects the parity bits. Now at the receiver, what we want to do is we want to check whether the received pattern Y is a code word or not. Okay, so that's what we wanted to do. We wanted to look at the received pattern and then decide, is it a code word or is it not? Okay, it has to be one of these 2 cases, and that's going to make our decision for us. Okay, so can we find a reasonable way to check whether we have a code word or not? Well, for a small code like this, we could just search the code, right? But codes in general here could have maybe the number of inputs bits here could be huge. I mean, it could be an IP packets which is 1500 bytes, and then the number of code words is 2 to the power of 1500, which is more than the number of atoms in the universe. Right? We have problems storing that table. So this table lookup is out of the question, right? So we need to have some algebraic way to compute this rather than do table lookup. Okay, so what we do then is essentially say, okay, if Y is a code word, then we know that the parity bits here corresponds to the data bits. So what we basically do is we take the data bits and then encode them and see whether those compute the parity bits which corresponds to this and check whether they are the parity bits that we received, because then it is a code word. Okay, so what we do here is we take the data bits, the data field, okay, in the received pattern, which is the data which was transmitted plus the errors, if any, right? Then we calculate the parity bits. So then we get the parity bits here, which corresponds to this field. Okay? And then we check those parity bits, whether these are actually the parity bits we received. Right? And then if they are equal, we say, that's fine, looks good. If they're unequal, we say, okay, error has occurred. Right? So if we would do this here, in this situation here, if I knew I had a systematic code, which I do, I would look at the data bits here that I received, and then I would compute the corresponding parity bits. And there is a way of doing that. We haven't talked about how to do that, but presumably there is an efficient way to compute the parity bits. Okay, and the parity bits, what are those? Corresponding to 0, 1, 0, 1. Okay, the parity bits are these things, 1, 0. Okay, so then I know that 0, 1 gives me the parity bits 0, 1. 1, 0. Okay, and then I check that. I compare that with the parity bits I received. And in this case, it looks fine, right? If I did it here, 1, 1 corresponds to the parity bits 1, 1. Just going into the table, you see that. And then I check 1, 1 against this, and I see, okay, they're not the same. So this is not a code word. Okay, so it's just a structured way of doing this. Okay? Questions? All right. So let's take 15 minutes and think about this. And I need to find my notes. Otherwise, I have to improvise the whole lecture here. Kan du trycka på den röda knappen till höger om batteriet där? Den ja, precis.